All right, so we just finished talking about the second derivative for multivariable functions and kind of the Hessian matrix that pops up, and now we're going to jump ship just for a little bit and talk about something else that is in actually section 4.2 for just a minute, called quadratic forms. Okay, so the definition here of what a quadratic form is, it's a function that has at most degree 2 terms. Okay, so you can see here that each individual term, so we have C, C11, C, all the C's are just coefficients. I don't know what they are, but they're coefficients. And then the variable component to each term has at most degree 2 when we multiply it out, right? So that's all a quadratic form is in n variables, okay? So I'm just going to say this is where each term is degree 2, okay? And it has to be degree 2. If there's a term that's degree 1, then we would actually say it's not a quadratic form. Okay, so just some examples here. Okay, what we might say are quadratic forms is something like x squared plus xy plus y squared. That is okay. We could do xy plus xz minus yz. That would be okay. Something that is not okay is something like e to the x plus x squared. Okay, clearly that first term is not degree 2. Similarly, x plus xy plus y squared, not going to work. Okay, and then the upshot of all this is that if you maybe rearrange it with a little bit of cleverness, you can actually represent that polynomial in n variables as a matrix of your variables times your coefficient matrix, okay, and then times the transpose, okay. So matrix multiplication makes this work out nicely, okay, and so that's kind of a nice, useful thing that we might use later on here in our first example, okay. So if I have a matrix like this, I can do the matrix multiplication. I can do these last two first, and when I do that, okay, so I'm going to have xy times, and then let's see, what do I get out of that? I believe I get x plus 2y, and then 3y, okay, and then I do the multiplication here, and I end up with x squared plus 2xy, and then plus 3y squared. Okay, so that certainly is a quadratic form. And similarly, now I'm given the quadratic form, right, and I need to go to that matrix form. Okay, so I'm going in the reverse. Okay, so this is perhaps one of the more challenging exercises. So I know that I should have something that looks like x, y, z, okay, and then my coefficient matrix here, and then I have another matrix of x, y, and z here, okay. So this could be challenging to fill out. What I'm going to do is say, okay, well, let's start with the squares, okay. Those are going to lie along my diagonal. You can go back up and look at the definition to verify this, but so I should have 1, and then 5, and then 7, okay. also, if you go back up and look at the definition, the matrix is actually upper triangular. Okay, so that means below the diagonal. Oh, I don't know what's going on there. Go away. Okay, there we go. So the matrix is actually upper triangular, so I should have zeros below the diagonal. Okay, so then I just need to kind of figure out, okay, well, where does everything else go? Okay, well, in the first row, the second column should just be where x and y correspond, so that would be 4. Okay, and then similarly 8 would go in the first row, third column, and then by process of elimination I should have 6. Okay, so this is actually really good, but I'm going to tell you this isn't the only answer. Okay, per the exact definition, this will work, but keep in mind that this could have easily been y or yx, zx, right? Multiplication is commutative. That is to say, instead, you could have had a matrix that was lower triangular. So you could still have the diagonal elements as 1, 5, and 7, and now you'd have zeros above, and you could also say this is 4 and 8 and 6 like that. Okay? But the fun doesn't stop there. That isn't the only other answer, right? I could have split this into, say, 2xy plus 2xy, or any combination thereof. Okay? It just so happens that I could have also had, let's see, I could have had 1, 5, and 7 still along the diagonal, but then split the 4 among the x and y components, and then the 8 would be split as 4 and 4, and then 3 and 3. Okay, so at the end of the day, I could have written it as that first one. The other ones would have been just as valid because I don't have any further information. Okay. However, that does lead us to a nice result, at least in the case where we're looking at quadratic forms and we're talking about that coefficient matrix being symmetric, right? Then there is only one such matrix. Okay. So imposing the restriction of symmetric forces our hand. All right, so then symmetric matrix S, and then we have X, vector X transpose, that symmetric matrix, and X as the decomposition of that quadratic form. Okay, so just as a quick example here, we saw this previously, this idea, so I can put the squared values along the diagonal. So 4, I don't have y, so that would be a 0, and then a 1. Okay, and then for symmetry, right, I have to take each of the coefficients and divide them by 2 and split them equally among their components. So x and y should have -1 and -1, and then x and z, so this would be 3 and 3, and then there's literally nothing that contains y, so that's all 0, and that would be the decomposition. Okay, and that's the idea of a quadratic form and a nice theorem to go with it.